know you didn't ask for it time. So you got your question.
What's that?
You got your 5 questions. I got all 5.
You do. Yeah, I'll have to figure out how to do that. And we'll let you ask your 5 questions. Bring them up, Michelle. This is we hadn't talked about that yet. That's okay. Okay. Gilbert's going to ask y'all questions. I need to answer them. Ask them, Gilbert. Very seldom use contacts. They very seldom use little relays. What they do is they either use an NPN or PNP transistor. So we have 2 types of sensors. What type did we say? 2 types of DC sensors. Now, I'm not talking about that 2 types of outputs a DC sensor can have. When I say a DC sensor, I mean one that's powered by DC and switches a DC signal. Everybody know? I thought we talked about that. We were just going through sensors. We didn't. We should have. The 2 types of outputs, or the 2 types of waves we can run, is with DC. And it all depends on where you are and what you do and how your company runs or stuff like that. I'll just insert a slide right here. We can come over here when we have DC, and we'll just draw 2 lines like this. These are what we call the power rails or the rungs, and then we come up here. We're going to connect circuits between these rungs. Well, I can come over here and I can put a control device. And right now, some of y'all hadn't had control. Well, let's draw it as a switch. Now, this is an electronically controlled switch. And then we come over there and we bring this into an input of a programmable controller. We'll just draw this as the load, and we'll just draw it as a block. Now, which one's positive and which one's negative? It's DC. Which one's positive, which one's negative? Don't make any difference. It's DC, you know. Depends on which way you want the current flow, right? So I could come up here and make this positive, and I could come up here and make that negative, and current will flow through the load. Okay, you understand this? Okay, current flows to the load. Now I could come over here, and I could put another switch and bring it into my PLC. I could come over here and put another switch that's electronically controlled and bring it into my PLC. I could come over and put another switch that's electronically controlled and bring it into my PLC. And everything would work, right? You understand? Everybody okay? Well, what's the common to the switches? What's common to all the switches? The plus. What's common to the PLC? Negative. So in in PLCs, if it's common to the plus, we call it sourcing. If it's common to the negative, it's called sinking. So what we have to do, if my sensor, if my PLC is wired to sync, then by George, I better buy a sourcing sensor. Because if I buy a syncing sensor, it's not going to work, right? You understand that? So, or I could do this. I could switch this to minus. I could switch this to the plus. Now my inputs are syncing and my PLC is what? Sourcing. So what we're saying is that I better buy the right DC sensor. This doesn't come into play with AC sensors. This is a DC sensor technology, right? You understand that? So what we do is we come over here and we buy these sensors. Well, how do I know if it's syncing or sourcing? Well, most of the time it's not put on. They don't call them syncing. So in PLCs, we call them syncing and sourcing. But what the DC sensor uses, it uses a saturated transistor. That's what it uses as its output. People might draw it as a relay, but it's not. It is either a PNP or an NPN transistor. Which one would you think I would use for syncing, and which one do you think I would use sourcing? Some of y'all had PLCs, and I make sure I teach this. What's a syncing sensor? An NPN or a PNP? Now, syncing's NPN, and sourcing is a PNP. So you got to know that, because when you go and buy the sensor, it don't say I'm syncing, and it don't say I'm sourcing. It says I'm an NPN sensor or I'm a PNP sensor. And that's the way PLCs run. So all our PLCs over there are DC. Their inputs are DC and the outputs are DC. So that means I got to know before I buy a sensor how that PC is wired. Some of them are some PLC. Some of the PLCs you buy them is either syncing or sourcing inputs. The predominant way that we run over here in the USA is we run syncing inputs and we run sourcing outputs. So that means I'd buy NPN sensors over here, right? And that's what they're doing. So the sensor goes out and senses what it needs to sense, whatever it is, whether it's sensing metal or whether it's sensing pressure, and then it generates an output. And it's got, instead of a solid state, they're called solid state sensors for a reason. So how do they output? They either saturate an NPN transistor. So an NPN transistor, this would be minus, right? And then my load would be, my output would be sent right there. And then the PLC, we would connect to this, and that would be my PLC input, and it would be connected to plus, and we saturate the transistor. Right, you understand? PNP, we'd come over here, and the load is connected right there, and this over here is connected to a big plus. I'm sorry, to big minus. No, it got to be a plus. And this is the way so here we output on the emitter, here we output on the what? On the collector. And that's basically the way the two types of solid state sensors work. Another thing that we need to talk about is that the problem we have with photodiodes, and of course we have to hook this into the circuit reverse bias, and we have to protect it with some type of resistor. And what do these guys do? Photodiodes? I wouldn't say it absorbs light. That would be like I get sunburned and I'm absorbing light. You're not absorbing light. I don't know if anything. Well, no, illuminate. Some of the what do they call them? When you turn off the light, it glows, but you don't glow unless you expose it to light. That might absorb the light. But what does photodiodes do? That was basically one of the questions Gilbert asked. He said a photo sensor. What this thing does is we put it in there, reverse bias. Y'all not impressing me, guys. Because we've already talked about these. So what a photodiode does is it varies its resistance with light. It's actually varying its leakage current, but if leakage current goes up, the resistance of the diode goes down, right? If yeah, we did that, but we did it, well, we kind of did it. We cheated. The problem with a photodiode is that we can't get a load out of that thing because the resistance is still going to be extremely high, right? So I can't run a load off a photodiode. I could use the output in a transistor where I get a gain, but they say if I'm going to take the output of a photodiode and run a transistor, we know that light can control current. So what the interrupter actually uses is a phototransistor. And so the light acts as the base. So the light strikes the base junction, and then it creates a current, a real small current. But what do we get out of a transistor? What kind of gain we get out of a bipolar transistor? We got 3 gains, guys. What's the 3 gains I could possibly get? Voltage, current, and starts with a P. Power. Okay. Now the ultimate goal is to get power gain. Why is the ultimate goal to get power gain? This is how much work I get. Right? You understand? So power is work. That's how much work I get out of that voltage and how much work I get out of that current. You know, as I could come over here and I could push against that wall right there, how much work am I getting? I'm getting 0 work. So to get work, physics defines work as a force applied over a distance. So that's what we're doing. We're moving current, right? The current is moving, which gives us our distance, so we get work. So you have to get work, then something has got to what? It's got to move. Everybody understand that? And work is work. I mean, hopefully y'all understand that. It's not working for the city of Bessemer Street Department and sitting in the back of a truck all day long. That wouldn't be, well, I don't know. It might count as work because you're in a truck and it's moving, right? and you got force with your butt sitting back there. But so guys, this is the stuff. This is just basic stuff of just understanding these things and how they operate and what they do. So photodiodes, you're not going to run into photodiodes that often, even though these were probably the first things we used in our photo detectors. Most of our devices actually use phototransistors. They're actually incorporated. So I guarantee there's probably 100% chance this guy up here is using a what? Phototransistor. And sometimes they'll bring the base lead out. So not only can you get gain out of it, but you can bias it the way you want to bias it. So if I was going to operate it in the active region, then I would bring the base out, and then I could bias it so I could get as much up here and up there. So what's the 3 regions? What's the 3 regions we can operate a transistor in? If we can saturate it, we can cut it off. And 3 is the active region. So which region is the radio in your car operating all those DVDs? Yeah, they operate in active. These, we don't use them apart. If I was going to always saturate a transistor, I would just I'll just hook it up, right? You understand? If I was always going to cut off a transistor, I'd just leave it open. So this is our switches right here. So this is where our digital switches operate. we either saturate it and make it act like a closed switch, or we cut it off and make it act like an open switch, right? So that's the switch. That's what we're talking about right now, is the switch. Later on, we'll get into the different classes of amplifiers. We'll see how we can bias these things so they'll pass an AC signal instead of a DC signal. And we'll see about that. But right now, we're looking at saturated, what we call a transistor switch, which, guys, are used all over the place. How many switches do you think there's inside this computer here? Bunch. Inside the microprocessor, in this one right here, I think this is an i5. I think of i5 as the dual core. i7s, there's over 1 billion transistors just inside the microprocessor. The memory, every memory cell, every memory bit is a transistor, at least one transistor. So this has got 8 megabytes. Most people say megs. I don't like that term. It's got 8 megabytes worth of transistors just in the memory. In the RAM, yeah. And that's not including the firmware, the ROMs in there. And then you got all the bus architecture, everything that controls the buses. The microprocessor is not designed to drive something. It's designed to put out ones and zeros out of all its buses. So outside of that, you got to run it into some device that provides the drive for this display, right? For all that kind of stuff. So there's all types of transistors. Good gracious, guys, I wouldn't even know where the number of transistors in your cell phone would be. They're probably not BJT. There's a pretty good chance they're FETs. But we'll get to those too. They're still transistors. So calculate this for me. So what do we want to calculate? You don't calculate beta. We could calculate beta, but I'm going to have to give you all that. Let's use a beta 100. So of course we need to calculate DRB. We need to calculate DRC. We need to calculate DCE. Of course, we need to calculate IB. We need to calculate IC. We'll calculate IC first. Don't put them in. Don't try to do them in the order of the way we're doing it. No, we calculate IB. On this one, we'll calculate IB first. That's right. Okay, so what volts did you use? How many volts did you use? 4.7. 4.3, right? So what we do is we treat this like two circuits. What we do is we showed you the equivalent circuit. Is I've got one single resistor circuit with a diode in series with it, right? This is going back to a power supply. This is my base circuit. What's that? Yeah. And then what we do is we take the collector circuit, and I know this guy, right? I know RC. And then the transistor is going to be one of these. and then my base circuit, and then I'll come over here and have this guy right here. Now what happens is this circuit sets the current in that circuit. So what it does, it sets the resistance of that guy right there, transistor. So this is the transistor of VJT. Or actually it's a transistor, FETs. If you understand this, FETs. So a transistor, a bipolar junction transistor, uses a current to control a current. So it's a current valve. So the more base current we put in, the wider the current valve opens. It lets more current flow, right? Which means the resistance goes down. The less base current we put in, the what? It closes the valve or moves the valve toward closing. And then, of course, the more resistance the transistor has. So there's a little formula that we use. What's the formula to calculate the collector current? So next we would calculate the collector current. That's 4.3. So IC has got to be equal to IB, and it's current gain, right? So it's going to be times something, right? So what is beta equal to? No, I mean, how do I calculate beta? I should have rephrased it. Okay, so IC over IB. My goodness. I know IB. I know beta. I'm just trying to figure out what IC will be. Can I transpose that equation to solve for IC? I hope not. Beta time. It's gain. So you're taking a small base current to get a large collector current, right? You understand? So we're going to multiply, right? You understand? We're going to multiply this. And since this is division by here, right? You understand? There's no addition that this thing would transpose to, right? You understand? So it's either got to be multiplied or it's got to be divided, right? So when I transpose that equation, I'm going to come up with an equation that multiplies. I'm going to come up with an equation that what? Divides. Collector current is a lot bigger than base current. So by George, when I go to collector current, I better multiply, right? So this is going to be times beta. So what would my collector current be? Huh? So it's 4.3 micro times 100, 430 micro. Sounds good to me. Because it sounded like you were 430 micro, just kind of questioning your answer.
I can't question calculator.
Well, you can too. Because the calculator depends on you hitting the numbers right. So if the calculator gives you the wrong answer, it means you entered the wrong numbers wrong, right? So now what do we know? Okay, so what can we do with IC? So I've got IC over here, so that means if I put a current meter right there, it's going to measure 430 microamps. We can get VRC because it's a series circuit, right? I don't know the transistor. The transistor is a variable resistor, right? You understand that? I don't know where it's set to. But by George, I know the current. I know what? I know the size of this resistor. What's the size of this resistor? 100 ohms. So I can calculate VRC. So what would VRC be? What? $43 millivolts. Everybody agree with that? So what would DCE be? Guys, we're dealing with DC. We're dealing, if I was to come up in DC, I said, I got a series circuit. Huh? VCE. Just don't look at a formula sheet. This is DC, right? And I said I got 20 volts applied. This guy's dropping 5 volts. How much volts would be dropped across that other resistor? 15. Okay, we got the same situation. I've got 43 millivolts dropped across that resistor. What would be dropped across the transistor? It's Kirchhoff's law. Kirchhoff's law says the sums of the voltages in a series circuit have to equal to the applied voltage. So what would it be? Voltage collector and emitter, what would it be? Yeah, we could say 9.95. Would be 9 because it's, oh yeah. So the transistors, huh? Voltage collector to emitter. Yeah. So this is the way you would measure it. This would be your watt, meter, common, and then of course this is where your red lead would go. So that's the way you'd measure it. So the transistor is pretty much well cut off if we calculate everything right. So everybody agree on the 4.3 volt here? Everybody agree on the 430 microamps? And then we came up with the beta. This is the beta I gave you, right? Where do we find the beta of the transistor at? Is it called beta in the data sheet? No. Huh? What's something else? And that's the problem. Most books teach beta, but the data sheet don't call it beta. But they call it the current gain. You'll see the current gain, which should give you a hint. It's called the hybrid forward transfer ratio with the emitter common, H sub FD. Little h, uppercase F, E, and the subscript, H sub FD. Now what's the disadvantage of using beta in any calculation for a transistor? So this transistor's cut off. We could screw around with it or change the size of the resistors. Problem we have with beta is beta changes with temperature. So that means, depending on which beta I use, I could have a transistor switch that would saturate in the summertime and not saturate in the wintertime. So we'll look and see how to design a switch. It's not that complicated. We won't use many more formulas than you should already know. Some of these formulas I should take off the formula sheet. Some of it. Ohm's law is not on there. Kirchhoff's law is not on there because why? You should know them. Those are things you should know. And all we're doing basically is just taking formulas that we learned in DC and just rearrange them to solve for the exactive circuits. So the only new formula we really added so far is what? Beta. And after that, what did we use? We used just Kirchhoff's law, right? So let's come up here and see if we can move this thing. So now we're operating toward cutoff. It's not quite, this would be considered cutoff, guys. So we need to do something. So to get more collector current, what do I need to do? Suggestions? We'll leave the beta at a 100. Yeah, to get more collector current. So our load's out here on the collector current. So this is the load right here. That's the actual load I'm trying to control over there. That base resistor is just keeping it sets the base current for it. That's this function. So this guy is not the load. This guy sets the base current. Sets is correct. So what do I need to do? To get more collector current, what do I need to do? Y'all are killing me, guys. I need to get more what? Starts with a B. I'm setting the beta at 100, so I'm keeping this constant. I get more base current. Good. So how do I get more base current? Make the resistor smaller or make the base voltage higher. Either one. So let's make the base smaller. So let's drop it down to, like 1K. You might even drop it down lower than that. Let's recalculate the circuit. Well, is it 5 milliamps? We're 4.3 milliamps. I see would be what? $430. Yeah. Some of these you can do in your head, guys. Especially when you multiply tens and hundreds and stuff like that. RC, VRC. $430 milli times 100 ohms, guys. $43 watts. That can't be right. Why can't that be right? Well, we're not talking about this circuit. You gotta see this thing as two circuits. You gotta see that as two circuits. I don't have a problem with this circuit over here. So the calculations for this circuit over here are right. Right, you understand? I'm trying to do another color. So this is one circuit right here. And here's our next circuit right here. Right? You understand that? So we finished the left circuit. We didn't drop over 5 volts within that circuit. But we're trying to drop over 10 volts in my collector circuit. Right? You understand? I cannot drop more than 10 volts in my collector circuit. So how many volts are we going to drop? 10 volts. That guy right there is going to drop 10 volts. Right? You understand? It's going to be 100 milliamps. I don't care what the base current is. You cannot drop more than you got applied. Huh? That's what you do unless you saturate it. If you saturate it, you cannot turn a water valve on more than the water flow you got. I don't care how big the valve is, right? You understand? So I can come into my house and go out there and put a big old valve and I open it 1/10 of the way and the water flow matches. Now I can open it all the way and I can't get more current flow than is available to me, right? So I cannot get more current flow that allows that resistor up there to drop the voltage. So if I come over there and multiply that beta times that 430 milliamps, I cannot have what? I cannot have, what did y'all come up and calculate? Huh? So what did your collect IC come up there? 430 milliamps. I cannot have 430 milliamps of current flow in that circuit. I cannot have it. Why? Because that would make that dang resistor up there drop how many volts? Huh? No, I'm talking about the 430 milliamps. 430 milliamps won't cause that thing to drop 10 volts. What did y'all say? 43 volts. Can it drop 43 volts? No. So what's the transistor operating? It's operating in what? Saturation. As soon as I do this guy, as soon as I calculate saturation, that transistor no longer has a beta of 100. The beta is going to drop down. Right? You understand? Because we saturated our transistor. But this guy's going to be saturated, which means we shouldn't have to worry what temperature is outside, right? You understand that? Now that's when we saturate a transistor, huh? The valve is fully open for this circuit. Now what's determining the flow? The maximum flow. What determines the maximum flow in the collector circuit now? But what device in the circuit is controlling the current flow? The load. The load. So the load is controlling the collector current. Once a transistor turns wide open, the transistor can't do anymore, right? Your water valve is turned wide open. So that resistor right there is controlling the flow. So now the transistor, so we went from cutoff, right? You understand? So we're dropping 9.95 across the transistor. Was cut off, right? Only had millivolts across the load, right? And now we're saturating. No, if it was below this. So we consider anything to be less than DCC. We consider this to be saturated. We consider anything to be equal to or approximately, but this guy here is going to drop less than a volt. If it drops the whole voltage, we consider it. So if it's equal to VCC. We consider it to be cut off. If it's between saturation and cutoff, we consider this to be the active region. Now, for the active region, we would like to put this at we'd like to put the collector at 1/2 of VCC. And so normally we would try to figure out how to bias it to get that at 5 volts. That means it could go up 5 volts, and it could go down 5 volts and still be without saturating or cut off. No, sorry. Less than 1 volt. I had other things. Thank you. If it's less than 1 volt, if voltage collector to emitter, so this is one of the most important measurements you'll make. That's what I should have said. If the voltage to collector emitter is less than 1 volt, we consider the transistor to be saturated. If VCE is equal to VCC, we consider it to be what? Cut off. If voltage collector to emitter is somewhere between saturation and cutoff, we consider it to be inactive. Voltage collector to emitter. What's voltage collector to emitter? That's the voltage that the transistor's dropping. What's that? Yeah. Yeah, so it's got to be somewhere between VCC. If it's close, so if I would come over here and the transistor's operating, if VCE is 6 volts, we'll say it's in active region, but it's operating toward cutoff. So anything above 5 volts would be operating the transistor toward cutoff. Anything below 5 volts would be operating the transistor toward saturation. That makes sense? So we would like to put it at half, exactly half, but that's usually impossible because I use standard size resistors. You understand that? So I could use a rheostat up there and I could set that sucker right at 5 volts with a certain base current, right? You understand that? And then when the base current went up, the voltage across VCE would go down, but I would have 5 volts up and 5 volts down, right? But the problem is, a rheostat, a 100 ohm rheostat might cost me $5, and a 100 ohm resistor will cost me 15 cents. Right? You understand that? So if I calculated, when I calculated the size of that resistor, you know, if it calculated 123 ohms, then I'd probably use either 100 ohm or go up to the next value, right? Depending on which direction I wanted it to operate. Are we okay? Yes or no? Do I have enough marks on there? Can you make this out? So go ahead.
So VCE, well, you knew from us.
As soon as you said 43 volts, I knew it's saturated because it can't drop 43 volts. All it's going to do, the maximum current it can handle, but not handle, the maximum current that will flow through the transistor will be when that resistor is dropping all the voltage. Because that's when the current flow in the transistor, the current flow in the circuit will be maximum, right? You understand? So if that guy up there is dropping, 10 volts, then how much is left to drop by your transistor? Nothing. So it's acting like a closed switch. Now it will never be nothing. A switch, it would be nothing. But a transistor is always going to drop some voltage, and that's why we say less than 1 volt. And normally in the data sheets, they'll give you what you should expect across a transistor when it's saturated. And what's nice about using a transistor as a switch is that when the transistor's cut off, it's producing no heat, right? You understand? And when it's saturated, it's producing very little, right? Because a switch, does a wall switch over there get hot? Not if it's good. There's no R. A wall switch should have no R. P is equal to I square R, right? So I've got 100 amps through there. Well, 100 amps squared times R is still what? Times 0 is still what? 0. If you got a wall switch getting hot, what does that mean? Something wrong with it. Yeah, you got a watt in that switch. You got an R that's not supposed to be in there. So either using a switch that's got too small contacts or that they become corroded and they do get hot. Wall outlet should not get hot either. If a wall outlet gets hot, how much resistance should a wall outlet have? It should have 0 ohms, right? You understand that? Or that we can measure. You know, everything's got ohms, but you know, we don't have our meters don't have the ability to measure down in micro ohms, right? So if you got an outlet that's getting hot, what do you need to do? You need to change it, yeah. Can't fix it. Those things are consumables. So they're all riveted or glued together. So this is called, this is in your book somewhere. In fact, the book teaches this a lot. This is called a collector characteristic curve. And a true characteristic curve, what it does is it actually shows a slope. So the transistor always has a what? It always has an R component. And so when current goes up, collector current goes up, then of course the transistor is going to drop a little more voltage even when it's saturated. When the collector current goes down, the transistor will drop a little more current. So this guy here has a slope. So what they do, and up here, this is IC. And then this right here is voltage collector to emitter. And then what they'll do is they'll come up here and they'll set the voltage at they'll set the voltage somewhere. And they'll start increasing base current. And then pretty soon it's going to do what? It's going to level off. No matter what we put on VCC. Now this is bad over here. So down here we'd have 0 IC. So here the transistor would be cut off. Right, you understand? So what this would show us, it would show us how the thing would respond, and these are the base currents right here. Makes sense so far? Y'all find this in the book? Now, of course, the problem we have, is that, and we'll show y'all later on, I can come up here and I can put a signal on this, and I can come up here and it takes it. Eventually, guys, right now we're going to deal with DC. But eventually we're going to have to introduce these things to what? Controlling AC, which they don't really, but we'll see how it works. So right now we're going to see how this thing would respond to an ACC. And when we come to that, we'll come back to this and show you how you can draw the AC signal over here and figure out what's going to happen in the circuit. It's really neat. This is called a what? So what the collector characteristic curve shows you, it shows you how the transistor responds for a different what? Base current. Well, what's so neat is once we have it at a certain base current, and nothing else changes, the voltage the collector emitter can change over a range between cutoff and saturation, right? And the output across the voltage collector emitter part, voltage applied, VCC, or a voltage collector emitter can change. It's not going to affect the operation of the transistor. Are we okay?
Is that in the book? Is that the saturation cutoff point?
Cutoff is over here, right? You understand? Here's when collector current would try to approach infinity. Of course, so if we didn't have some type of, notice that, so here the collector current would try to approach infinity. So it's moving towards saturation. So we couldn't run this thing without a load, because if you saturate it, it becomes almost 0 ohms, then you'll have a short circuit and you damage the transistor. So up in here would be towards saturation, right? Makes sense. And then out here would be cutoff. So here IC is equal to 0. Okay? Makes sense. So what we're saying, if your base is constant, your base current is constant, IC is going to be constant, not exactly because of the variations, even though voltage collector emitter is doing what? Changing. So if I was to follow this over, and we'll show y'all how we can do this, unfortunately, they don't give the collector characteristic curves in the data sheet. But they should give you enough information so you can develop them if you need. The only thing we're going to do is when we develop them, we're not going to consider the slope, this little slight slope because of the resistance of the transistor itself when it's on, right? We won't consider the slope. So our characteristic curves will come up here and they'll go up and they're either cut off or on, right? And then we'll come up and do what? Ours will be straight across. Because we don't know the resistance of the transistor when it's on, right? That makes sense. But this is going to be an approximation, so we'll get an approximation. Transistors, we're going to use a lot of approximations because the transistor's not perfect, our resistors are not perfect, right? You understand that? So that means we're going to use a lot of approximations. Approximations still means we're going to calculate our perfect math, right? You understand that? But we're going to know that our measurements and our calculations are not going to be the same, but they should be close enough so we can figure out what, if it's wrong or right. Yeah. Unfortunately, you're not going to have to do a lot of the calculations that we learned here, but what we're going to still teach them to you. So when you get out there and you look at these voltage measurements and stuff, you understand why they are what they are, right? And what you can do and how you can look and how you check these circuits out. So this is where transistor as a switch. This is where we'll do it. So what we're going to do now is we're going to look at our transistor as a switch. And then we're going to look at the transistor as an amplifier. Which is active region. We're going to look at the active region. So a switch is when we operate the transistor, and we're going to look at a single power supply bias. So very seldom, well, that's not true. A lot of times, so if I go over on all these transistor sensors over there, they're all PNP sensors, right? Because we're sourcing, because the inputs are syncing, right? You understand? Are they operating on multiple power supplies? No, they're operating on a 24-volt supply. So most of the time when you get into these guys, you're going to have to figure out how to make them work off a single supply. The only time we would probably need 2 supplies if we was trying to generate an AC signal out using solid-state devices. So base bias is the most common use. Base bias, and we'll look and see what that means. So we got 3 ways we can bias transistors. What is bias in solid state? As we talked about this several times. What is bias? How would you define bias? Okay. What does that say? A. What does that say? DC. Voltage. Applied to a semiconductor. to control his conduction characteristics. And that might not be the same thing I gave you. So bias in solid state is a DC voltage that we apply to these devices to determine how they work, how much current. So we got two biases. What's the two types of biases we can do? Forward and reverse. So a diode, if you reverse bias, it does what? It cuts off. If it forward biases, it cuts on, right? In transistors, we bias it to operate at saturation. We bias it to operate at, well, understand it. When we use a transistor on a switch, we're using two of the regions. And what's the two regions? If we operate it as a switch. Cut off and saturate. Okay, you understand that? So we bias it to be able to switch between them. So what we do to cut it off is we just turn off the base current. So 0 times beta is still what? 0. We get 0 collector. To bias it into saturation, we put enough base current in it to ensure saturation, no matter what temperature it's at, right? We'll show you how to do that. So what we're going to do here is we're going to bias the base. We're going to set the base current. So this is the one most likely, most often used as a switch. Base bias, BJT switch design, establish the voltage and current. What determines how much collector current we need? Yeah, how much collector current we need? The load we're trying to turn off and on. The load we're trying to turn off and on. So first of all, we'll look at the data sheets. That would determine exactly which transistor I would try to choose. What load are you trying to drive? What voltage, this determines what voltage you need, right, to run the load. And it's going to tell you what current you need. And of course, the load is being driven by IC. Right, you understand? If I know IC, and then I know the beta of the transistor, then I know how much base current I need to saturate it, right? You understand? Cutoff is no big deal. Whatever base current I've got, if I just take it away, the transistor's going to cut off. Understand? So what we're going to figure out is what I need, given my power supplies, what size base resistor over I need to do what? To saturate the transistor. Choose a transistor that will supply the current when saturated and block the voltage needed by the device when the transistor's cut. So it's just like a diode, guys. You cut that transistor off, you got that voltage to collector's emitter. It's acting like an open switch, but it's not an open switch. There is a path through there. You get the voltage up high enough, it's going to break over collector's emitter. What do you think is going to happen to your transistor? And what is it going to do? Well, the problem we have with solid state devices is they could fail different ways. So they could open, or they could short, or they could become extremely leaky, which means they always conduct a current even when you try to cut them off. So this is what we're going to do. So we're a transistor. So we're going to call these things SAT or SAT, right? So what we're going to do is that there's only, when we look at the data sheet, y'all bring up the data sheet if y'all got access to the internet. And we're going to look up just the data sheet of a 2N 3904. I was trying to transpose the numbers in my head. So the 3904 is a JEDEC registered transistor. So guess what that means? Open source. So that means anybody can make a 3904. As long as they take this data sheet and make their transistor meet those specifications. So all the transistors that we're going to be dealing with this semester are open source. Come on, come on, come on, come on. So where are we going to find our data sheets? In this data sheet, right? And then we're looking for a 2N3904 right here. It's an NPN-BAT. And then we're looking for beta. The beta is H of FE, the DC current gain. So even though they don't call it beta, just from the name they give it when the transistor's turned on. So we notice this beta is all over the place. The maximum beta we could ever have would be what? 300. The minimum beta we could actually have is 30. So which one of these is guaranteed? Guaranteed. The transistor is guaranteed to have at least one of these. 300 is not guaranteed. The guaranteed is the maximum. Right? You understand? No, the guaranteed is not the maximum, right? Yeah, so the minimum is guaranteed. This sucker is guaranteed to have 30, no matter what situation we operate in. It's guaranteed to have 30. That makes sense. So if we want to ensure a transistor saturates, which beta are we going to use? The guaranteed. We're going to use the minimum beta of the transistor. Are you okay? Yes or no? So it says IB sat, the saturated base current is going to be equal to that. It's saturated. How are we going to calculate the saturated collector current? No, how are we going to? Huh? Don't look this. Because this is calculating values inside my transistor. Right? This is used to calculate what resistors we need to get that. So we don't want to transpose this equation because this is going to be what? What are you looking at? So what determines IC sat? Okay, y'all are looking at this formula. I'm trying to ask y'all, I'm designing the switch. What determines my saturated, what determines my collector current? The load, right? So what I got to do is I got to run the load. So what do I need to know about the load? The current is designed to run in. So we need to know the what? We need to know the current required by the load. And what else do we need? We need to know the voltage. So my voltage will set the size of my VCC, right? So my VCC has got to what? Provide that voltage. And then, of course, I've got to choose a transistor and, of course, a power source that's capable of running that current. Y'all understand that? Well, let's just look at it. Let's just design one. What do we want to run? Let's turn on the LED. So I got an LED. Okay. So the circuit would look like something like this. We're going to use an NPN transistor, right? And we're going to try to use a 2N3904. Then we're going to come up here and I'm going to take my LED and put it right here. And this is going to be connected to circuit common, right? So we got to turn it this way. Lightning diode. I got to put a resistor right here, protect the diode once we saturate it. And then we can come over here. Since I'm using a resistor up there, we can use what voltage y'all want to use. The VF of an LED is, we're going to use about 2 volts. And then the I of the LED is usually around 10 milliamps. So we'll come up here and use the resistor. This is going to be this source right here. Okay. And we can use 10 volts right there. We can use that. Why? Because we're going to use that resistor up there to drop all of them. Oh, laughing. How's things? I got your text. Didn't Nancy send me? So what we're going to do? How would I bias this with one power supply? With one power supply, not with 2 power supplies, with 1 power supply. And you said forward. I mean, you're right. We have to forward bias. Here's my drop-in resistor, right? What I'm going to do is I'm going to come over here, and I'm going to bring this out right here. And I'm going to put my other resistor right here. Right now we'll call this RB. We'll call this RC, even though it's not connected directly to the resistor. Then what I'm going to do, to saturate it and cut it off, I'm going to come right here, and I'm going to connect a switch. And that switch could be coming from anywhere, but right now we'll just use a switch. So when the switch is closed, what region would the transistor be? Yeah, because IB would go to 0, right? Yeah, when it's closed. You go cut off, right? You understand why? Well, when this switch is closed, the base is connected to common. So VB is going to go to 0. Right? You understand? VB goes to 0. How much current flow we're going to have? None. Right? You understand? Now, when I open the switch, VB goes to whatever that resistor up there allows to flow. Right? You understand? So we're going to have to choose a resistor now that's going to drop what? How much voltage is it going to need to drop? No, here's the power supply. We're running it as a switch. Not at least. It's got to drop a certain voltage. What's it got to drop? RB. No, we don't want 5 volts on the base. If I measured 5 volts on the base of the transistor, I told her what. This is nothing but a P-N junction. How much does a P-N junction drop? Silicon. 7. Okay. So that means I got to get at least 7/10 of a volt down there to turn that sucker on, right? You understand? So how much does RB got to drop? 9.3. So RB's got to drop 9.3 volts. So VRB, we figured that out without even picking up a calculator, right? Okay. So we got everything we need, except what? Yeah, it's just a p-n junction. So my current path, by the way, I'm not going to draw electron flow. I'm just going to draw the current path. We call it signal flow. Here's this circuit right here. That's that circuit right there. Now this circuit is this circuit over here. Now you can see the two currents flowing through the emitter, but we consider them to be different, right? You understand that? And so this shows you which is the highest current flow in the circuit. According to Kirchhoff's law, the sums of the current flow into the junction have to equal coming out, right? This one has to equal that. So we have base current, we have collector current, and this is the sum of the two. So the emitter current is the highest current. Base current and emitter current are practically equal to each other. But, okay guys, so where do I need to go from here? Well, we gotta make something first. We gotta say, okay, this thing depends on the beta of the transistor, and it's the minimum beta, so we know that's 30. Now we got enough. Now we got enough to solve this. Right? You understand?
We would give a circuit like this on the test, and all I had to do is find the 3904 and get beta off.
Get the minimum beta. And why we're using the minimum beta, because we want this thing to saturate in Alaska, and we want it to saturate in Hawaii, right? You understand? If I was selling this thing. If I was in an airplane, I wanted to saturate at 32,000 feet. I wanted to saturate when they're sitting at ground level. So what happens, the problem we have with beta is it varies, right? You understand? It varies. It's not a fixed value. It varies depending on how much collector current you have, and it varies around this thing. So there's only one beta that's guaranteed. Now, when we get into the active region, what we're going to do is we're going to set the beta of the circuit. So it's not going to what? It's not going to vary. We can make it on this one, we can make it 30, or we can make it close to 300. We're going to set the beta. Right now on a saturated switch, we're kind of set the beta, but we're going to set it, it's going to be a little lower than 30, right? Because we're setting the beta. Minimum beta don't mean you can't operate it below that, but we'll show you what we're doing. Are we okay? So where do I go from here, guys? Let's see. What do I know? I got this nice little formula. Beta is equal to IC over IB. What do I know? I know the beta. No, I don't know IB. IB's what I know IC. I know IC sat. We call this saturated current. This is what we're going to saturate this thing. So I know two things. I don't know the base current. But can I calculate the base current? Okay, so what would the formula be for base current? If we transpose IB is little. IB is little. IB is always little than collector current. So it's got to divide. We got to have a division formula over here, right? You understand? So I like this one. If it's on top over here, on bottom down here, we just swap them. So IB would be equal to IC divided by the beta of the transistor. So this is something you got to understand. You know, if all you're doing is, if you got division, there's no way in the world you can get a multiplication. There's no way in the world you can get addition, right? And then transposing these equations. I know if it's on top over here, these two are multiplied. If it's on bottom, if it's on top over here and bottom over here, I just do what? I just swap them. I learned that trick a long time ago. I don't even use that little formula wheel, because that's what I learned. But if you have to use it, that's fine. So what would my IB need? What would I need for IB to ensure this thing saturates? IB, so what would I use? IB would be equal to, we're trying to get 10 milliamps over here, and we got a guaranteed beta of 30. So what IB would I need? $333 microamps. Everybody okay? Look all right? Okay, so I've calculated my IB. What can I calculate now that would allow that current to flow? The resistor side. So R would be equal to what? I'm sorry. R would be equal to what? V over I. What's that? What's that? Yeah, this is what we're dropping 9.3 volts, so it's going to be not the source, it's going to be that right there, right? Okay, because of the P-N junction right here. Okay, so what did y'all come up with? Listen, y'all called it out, but what's that? Okay, is there a 28K resistor available? So if this is not a standard value, what will we do? Will we go up or go down? Huh? Why? You're right. Y'all hear what Damien said? Are you okay? What we said is that what we're going to do is we're going to use a standard resistor to saturate this thing. So if this calculation doesn't fall on top of a standard resistor, are we going to go up the next value or go down the next value? Why? Well, the problem is that if you go up, then we calculated for a beta of 30. And once you go up, then your beta's not guaranteed anymore, right? You understand? If you go down, then you're going to really saturate because you're putting more base current than 30 allows, right? You understand that? And you're set now. So you'd always round down. Not round down, go down.
So when we calculate the resistance, we use the 333 micro instead of 10.
We're on the B? RB, yeah. All right, you on the right side? RC, we go ahead and calculate RC too. We forgot to calculate RC. Thank you. So RC will use 8 volts. Why? Because the LED drops what? 2. Transistor's supposed to drop 0, even though we know we can't do that. So 8 volts, 10 milliamps. What's that? Yeah. And what would we round up or round down? Here we would round. Y'all understand? We'd round up if it's past 0.5, we'd round down if it's not a value. If it falls right on the value, we'd put it on there. Right? You understand? Yes or no? It's an LED. If you put a resistor in there just slightly too big, it won't glow as bright if you put it in there. As long as you don't exceed the maximum current on the LED, you're okay. And you've designed your first saturated switch. We'll show y'all later on how we could design a circuit where you can put a lot of LEDs in series with each other, and if you add them, the current stays constant. We'll show you how to do a constant current source, which means you can put one LED in there and it will conduct. You put 2 in there, it will conduct the same current. until you run out of voltage over there. These guys are really, really neat. So what we're doing is we're using this to control this. So we're using microamps to control milliamps, right? You understand? So we sacrifice a lot of the beta on the saturated switch, but what we're trying to do is guarantee that it saturates, right? Makes sense. We have transistor switches all over the place. So this right here could be a little tiny switch, like a little tiny push button. And you're over here controlling a pretty good deal of current, right? You understand that from a very small control device. Okay, guys, let's take a break. Over and let me know. Are we okay? Don't want to use another? Make another? By the way, what's another thing that's really, really nice about a transistor is we can use two power supplies, right? You understand? Huh? Yeah. So what happens is like digital, the minimum high we can get out of a digital is 2.4 volts. But I need to run a 12 volt light. So I could design my input of my transistor to look at 2.4 volts, right? You understand? If the voltage goes up, the base current will go up, and I could size that resistor for 2.4 volts or 1.7 volts, right? You understand that? And then I could run a 50 volt supply if I choose the right transistor, just by going through the transistor, right? So we can design these things to run off one power supply by the way we hook up our base resistor, or we can supply it require it to run off of another supply. So what I could do most your TTL digital gates can supply up to 10 milliamps. On a base, that's a lot. That's a lot of current, right? Because of the switch we have. But we could we could shift this back the way we had it before, and then we can come over here and put our base resistor right here. And then we would come over here, and this would be a digital circuit over here. So this could be digital over here, or what we call TTL compatible, which is transistor logic. TTL runs off a 5 volt supply, but its maximum high voltage, its minimum high voltage is guaranteed. 2.4 volts is guaranteed. So that's what we would calculate it for, is 2.4 volts. If it's outputting 3 volts, it's no big deal. Base current would go up. But once the transistor's saturated, the base current don't make any difference once it's saturated, right? Well, we just don't want it to go down below saturation. So here I could take a transistor and hook it up to a digital circuit, and I could drive a load that requires 24 volts, right? You understand that? So we can use these things to go from one power supply level over to another power supply level and run a load, right? You understand that? Or we can operate them off a single power supply. Just about everything in the digital world tries to maintain digital TTL compatibility, especially when it comes out out of the device. So your microprocessor operates inside the microprocessor. The microprocessors now have 3 voltage levels applied to them. The lower the voltage level is, the faster the guys can run, because they don't have to switch it as far, right? And then, but when it gets to the pins that's driving other things, they're usually TTL compatible. So normally we wouldn't even need this unless we were really, really running low. So let's jump in and let's look at the data sheets and explain. So the next thing is amplifier. We're going to look at the different ways we can bias the transistor. And then right now what we need to do is go and look at the data sheet and let's explain its measurement. some of these. No, we're doing base bias because the bias resistor is in the base. RC is not really a bias; it's a load, right? You understand? So the bias we're using now is bias. So the base determines the base current in this situation is the one that's totally in control. The base current is always totally in control of the collector current, right? You understand that? But how do we get the base current? Do we get it from the collector? And we'll look at that later on and why these are called different things. I thought I had backboard up. So we'll go to backboard and we'll just look at the one that we're going to be dealing with. All of them are pretty close to the same though. So if we understand the ratings on the 3904, then we'll be able to understand them on different bipolar transistors. They'll be a little different in now. A lot of transistors are made in what we call complementary pairs. They have the same specifications as they're opposite. So up here, if a rating's positive, down here it's negative and vice versa. And we do that when we get into a circuit that has to actually generate AC, and we'll see where a complementary pair comes into place. We'll start out playing with a 3904. And then so the first ratings. First of all, the one that's most important is absolute maximum ratings. That means operation is not guaranteed, but the device will not be damaged. So your operating characteristics is somewhere between here, right? You understand? So the absolute maximum ratings does not guarantee it's going to operate right. It just guarantees it's not going to do what? Damage itself. So VCO, what this stands for is the voltage collector emitter with the base open. So the transistor's cut off. So, and then we're going to start raising that voltage between the collector to emitter, and we're going to find out where that circuit breaks over. So this guy here can handle what? 40 volts. Voltage collector to base with it open, with the emitter open, it can handle what? 60 volts. Voltage to emitter to base, this is a reverse bias voltage, right? Because notice they say we're measuring from the base to the emitter instead of what? Yeah. So this is a reverse bias voltage. All these voltage emitter to base with the collector open, maximum what? 6 volts. So that means it's reverse bias, because if it's forward bias, it drops 7/10, right? If it's reverse bias. Everybody okay? The maximum it could drop is 6 volts. It depends on what you put on it. The maximum you can put on it is what? 6 volts. If you put 3 volts, it's going to be cut off, but it's not going to be damaged. If you put 0 volts on it, it's going to cut off, but it's not going to be damaged. If you put above 6 volts on it, it's not guaranteed not to be damaged anymore, right? It don't mean it's going to crap at 6 volts. It means 6 volts is guaranteed. So that means they took thousands of these and they broke these things over on purpose. And the minimum they ever had them break over was 6 volts. So that's what we're saying. This is the minimum. I mean, this is the maximum you can put on it. If you go above 6 volts, it don't mean it's going to crash. It's just not guaranteed to crash. The analogy I use is like a tack gauge on a car. So if you ever saw a tack gauge, it's got a red line on it. So as soon as you go across that red line, is the engine going to blow up? It's just not guaranteed not to blow up on you, right? So they've tested this engine out over and over and over again. They've deliberately destroyed these things and see what it could do. And they figured out the minimum where these things started failing at. They didn't use the maximum, they used the what? The minimum. So all You know, as long as you operate the code below that red line, it's not gonna sling apart because of overspeed. Doesn't mean you're not gonna blow it up if you don't put oil in it. You still got problems. When we store this thing, we should store it anywhere between 55 degrees minus 55 degrees centigrade. That's cold. That's really cold. And then up to 150 degrees. You shouldn't store these things above that, right? Make sense? You okay? This is very important. This is continuous. This is our saturated current right here. This is the maximum current this guy should conduct when we saturate it. $200 milliamps, which is pretty good. Okay? PD, here's our power dissipation. This guy can saturate if it's operating at 25 degrees centigrade, which we consider data sheets. You're going to see in solid state data sheets, this 25 degrees centigrade is pretty common, which is around, I think, around 72 degrees Fahrenheit. I'm sorry, I need to say Celsius. Right? You can tell I'm old school. So total dissipation, and it says we have to dirate it 25 for every 25 degrees above. What's the rating? 20. Dirate above 25 degrees Celsius. So many milliwatts per degree centigrade. So it's just like what we looked at before, right? Are y'all okay there? So as long as I operate it below 25 degrees centigrade, then the top one would be met or better, right? So this guy here can actually dissipate, depending on which version you got. The 2904, we got the plastic, so that would be the one all the way on the left. Or would it be? The MMBT 3904 could get us, it's the lowest, right? 250. And then the PZT 3904 is 1,000 milliwatts, or 1 watt. And the 3904, we got the 2 in 3904, yeah, so it would do what? 625 milliwatts. Now what this comes into play is if I got the transistor saturated, which means I operate it above this, then I will never ever get this. So what we do for the saturated switch, on the saturated switch, we're concerned with this. In the active region, we're really concerned with this because now the transistor is dropping a voltage. And if it drops a voltage, then it's getting hot, right? You understand? Because P is equal to I times V. If the transistor is dropping less than a volt, it's going to dissipate very, very, very little power. You know, if it's dropping 15 volts, and you got try to put that current through it, what's it going to do? It's going to burn it up, right? You understand? Are we okay? Yes? Okay, electrical characteristics. This is basically what we need. Breakover voltage, common emitter, so that you notice these are the same as the maximum ratings. Are we okay? That makes sense? H of FEs, this gives us an idea, but every one of these are at a voltage collector to emitter. So all we really know, and a certain current, all we really know is it's going to be somewhere between what? That and that. We'll never see maximum beta. And right, you understand that? We'll never see that. All we know is going to be somewhere between what? 30 and 300. Voltage collectors emitter, saturated. So this guy, right, at the 50 milliamps, we should expect it to be a maximum of what? 300 millivolts. Right? Or if it's operating at 10 milliamps, we should expect it to be 200 millivolts. So this guy's still going to drop a voltage. So if you got a transistor turned on and everything else is okay, and you measure 0 volts across that, then something's bad. Right? I mean, something's shorted. DCE, okay, DBE sat, that tells us, okay, when I saturate this thing, we use 7/10 of a volt, right? You understand. But we know now that it actually is a slope. So it's telling us typically minimum it would ever be would be 650 millivolts, right? But it could be all the way up to 950 millivolts. That makes sense. But if we use 7/10, that's why 7/10 is an approximation. On the last test, I say a diode will always drop 7/10 of a volt, and some people call that true. That's the trick. But the question said will always drop. It might drop 7/10, but it might not, right? Are we okay? Small signal gains. These are all AC characteristics, active characteristics. Bandwidth product gives us a feel of bandwidth of the device. What do we? Y'all hear bandwidth all the time. What in the world does bandwidth mean? All you know is that the more bandwidth I have, the faster it is. But what is bandwidth? It is speed, but a bandwidth is a range of frequencies a media. What is media? Now, media is what information flows through, right? So when we're talking about signals, we'll be talking about media, right? You understand? So this is the range of frequencies that the signal can flow through reliably. And it's a 3 dB. We talk about dB in this class? Yeah. What's been around for years, especially in engineering technology, is we always deal with very large and very small numbers. So we know that we deal with scientific notation and engineering notation. If you understand those guys, you understand dB. It's just what dB does. It's an exponent. It uses exponents. But all it deals with is an exponent. The base of an exponent will always be 10. And then we're going to raise that to a number. Now, how I got this name, I don't know. But this number we raised to, they started calling a bell. Now, don't ask me. I think because it was originally used for sound volume. So I guess they compared it to like a sound of a bell. I don't know. Some of you might research that. So what we could do is we could take any number. So 3 bells would equal to 10 to the third, which would be 1,000. I'll follow that so far. Now the problem we have is that, and this is the log, right? So everybody got a log key on their calculator? LOG. Enter 1,000 and hit the log key. So that's 3 bells. That's what the log is. This is what we call a common log. We have a natural log, which you need to stay away from. It's 2.731, I think, raised to some power. How they came up, but natural logs we use for something that varies in a curve. So we don't use natural logs. We don't use natural logs in this class. So if you wanted to calculate the charge rate of a capacitor, it varies in a curve. If you wanted to do it precisely, you'd use natural log. But we're not going to look at that. So we're using common log. So you can enter any number, and hit the key. So let's say 1,563, and see what the log of that would be. Oh, keep going. Wait, 958, what? 97? Okay. So, what do you think we're going to do with a number that could go on forever? We could use scientific notation, but we're just going to round it. It's just like your resistors. It's just like all your math. We round. We tell y'all in DC to round to I don't know how many decimal points. Here we're rounding to 1 decimal point. So we could come up with answers that are ridiculous, right? You understand? So we're going to round this. But what they do is they take the Bales and they multiply it by 10. And we move it right there. So it's real easy. You just move it right there. And then you round it to the maximum I've ever seen is 2 decimal points. And you would call this 31.93 D, lowercase d, B. And that's what a decibel is. It's the Bales law.
I thought it was 10 cents. One cent, decibel is 1 cent.
It's 10 times your Bales. 10 times your Bales. So it's 10 times your log. When you hit log, you take that answer and you multiply by 10 and then you round it. Usually 1 decimal point. Now the problem with rounding is that you notice if you look at your calculator, this 10 to the x is somewhere really close to that. Don't y'all have a 10 to the x key? Well, what we can do is you can take that Bale and hit the 10 to the x key, and it should come back and give you 1,563. That's what it is. That's why they're right there together. Right? You understand? But the problem is I've got numbers where the decibels are going to be so big, or the Bales are going to be so big, that eventually even my calculator is going to start rounding. So that means if I come up here and I take this, so what would I do here if I wanted to find the actual number? I would shift that sucker to the left 1 point. Now I've converted it back to Bales. And then I would hit my 10 to the x key, and then I would see what that comes up to be. It's not going to come up to be 1,563, but it's going to be close enough. Eventually we're going to round, right? You understand that? Understand. So all you do for a decibel is you take the log of it, the number you're going to, right? And do what? Take the decimal point and shift it 1 to the right and call it dB, and then round. So you'll never see a decibel that's carried out to 15 digits. If I'm going to carry it to 15 digits, I'll just use Bales. Right? You understand? We do this as a method of rounding. It's just a method of rounding extremely big numbers and extremely large numbers. We use this in signals all the time. I mean, we use it in communication systems all the time. They'll talk about a dB loss. If you get a minus dB, you know you got an attenuation. You got a loss. If you get a plus dB, you got to know you got a gain. And you got a pretty good feel. You know, if I've got 10 to the third dB, I know my gain is about 1,000. If I got between 10 to the third, 10 to the fourth, I know it's somewhere between 1,000 and somewhere between 10,000. So I get a good idea. Just looking at the dB, I have a pretty good idea where my answer should be at, right? Without picking up a what? A calculator, right? So that's decibels. It's just another way of representing big numbers. Now, it was originally used in audio systems to try to give us the amount of sound energy that was our ears could actually pick up. But it's moved into just about any communication system, whether it's electrical or whatever, which is pretty neat. So what we do is so when we calculate gains, how do we calculate a gain? How much gain we get? This formula is, we've already talked about that. How do we calculate the amount of gain we get out of a system? mechanical gain, electrical gain, any type of gain in the system. Out over in, beautiful. Out over in. And this is gain. We never get more work out, but we're going to gain something, right? You understand that? So work out equals work in times efficiency. And nothing's got an efficiency. So that's the formula. So work in should equal work out times efficiency. And efficiency is always going to be less than 1. There's nothing 100% efficient. This is true. This is, it's going to be less than 1. Can't be. We can't have 0%, right? You understand that? So everything's got an efficiency, so this is work out equals work in. So, what would be my voltage gain? How would I calculate voltage gain in a system? I would take voltage out divided by voltage in. By the way, what we call gain in formulas is we call it A. So anytime we see A, this means this is the formula for some type of gain. And then we put the little thing down there indicating this is voltage gain. So what would be current gain? So it would be AI, right? What would the current gain be? I out over I in. And what would a power gain be? Yeah, power out divided by power in. Which one of these gains are the most important? Power. Why? But what I would like to do is I would like to come up here and figure out a way that I could. So if I was going to calculate in this, I know this is backwards, but this is the way we get it. So AD dB would be equal what they say. They say log 10 V out over V in. So that would calculate. Actually, what you have to do, this is the formula, but you take V out over V in, you take the log of it and multiply it by 2. And that'll come up and give you dB. So what would current gain be? AI dB would be equal log 10 I out over I in. And then power gain, of course, would be AP equals dB log 10 P out over P in. Are we okay? Now you got to enter your calculator backwards, right? You understand? A conventional calculator, not what we used to call them reverse Polish, where you enter the formula. If you enter the formula, this is what you'd enter, right, with that type of calculator. But most of ours are standard calculators, and we'd have to, first of all, we'd have to calculate the V out over V in. Then we do what? Take the log, and then we multiply it by 10, but this is the formula. Now, what I'd like to do is I would like to go directly from voltage gain or current gain without going through some more formulas. Can I do that? So what's the relationship between power? So if I double the voltage to a circuit, what happens to the current? It doubles. So the voltage always varies with the square of the voltage or the square of the current, right? So what we can do, this is actually converting it to dB. So let's go 10 to the first. What would that be? That'd be 10. 10 to the second would be what? 100. So what we're saying is if I do 10 to the second, it's the same as squaring, right? You understand? Okay. Now in dB, that would be 20. So 10 bells would be equal to 20 dB. Y'all follow me so far? So, huh?
So if it was 10 to the fourth, then 40.
What's that?
So you have 10 to the fourth, that'd be 40 dB?
Yeah, that'd be 40 dB, right. And that's what we're saying. All you have to do is just move the decimal point to the right. But what we're dealing with, the square of the voltages, right? The square of the current, right? You understand what we're saying? So what I can do is I can take this formula right here. I'm sorry, this formula right here, and I can say dB is equal to log 20 times V out over V. So I took my voltage gain, and that's going to be the same power gain. That's how you do it. I just squared my answer. So if I knew the current and if I knew the current gain, I could calculate the power gain by using what? The dB would be equal to what? Log 20. Y'all know what? So 20 squares your answer, right? You understand that? So these are power gains. Now, the bandwidth, this is what we got off to. The bandwidth comes from the fact that if I half the voltage to a circuit, what would happen to the power in the circuit? If I half the voltage applied to a circuit, these are DC, if I half the voltage applied to a circuit, what would happen to the power in the circuit? So let's go. Okay, look at this. So let's say I got power. My power is equal to 100 volts times 100 amps. What would my power be? Well, let's say I come over here to the same circuit. I drop this down to 50 volts. Voltage and current to a circuit are directly proportional. If I half the voltage, I half the current. So my current drops down to 50 amps. What's my power to the circuit? What? Yeah, 2,500. So power varies with the square, right? It's not, if you double your current, you quadruple your power. So if it goes down, it's 1 over the square. If it goes up, it's the square, right? You understand? And a lot of people don't understand this, guys, you know. And, huh? So if it goes down, it's 1 over the square. If it goes up, it's times the square. So if it goes up, if it triples, the power would go up times 9. If the voltage drops down to a third, it would go 1 over 9. It dropped down to the 9th of the power. It's 1 over the square. It's always 1. So if it goes down, it's 1 over the multiplier, right? The square root. If it goes up, we multiply it by the square root. So power varies with the square. So what we're trying to do is we're trying to get power. Power. So when we deal with bandwidth, how much we can actually apply, then we're going to come over here and we'll start off if this is frequency. And then this is voltage. It's hard to measure power. It's real easy to measure voltage, right? An oscilloscope, that's all it measures. So what we'd start off with is we'll start off with 0, and eventually the amount of frequency I get through would start rising. And then eventually it would level off, pretty level. And eventually it would get too high and it would drop down. And this right here is what we call the bandwidth. Yeah, we call this F2 and we call this F1, but F1's got to occur. Now, where would you think, and the cutoff is 50% of the power. So the cutoff frequencies, where these things start dropping down real fast, we call that the cutoff frequency. Where would you expect it to occur relative to voltage? So let's say this is 10 volts, maximum. Gives me my maximum power, because the voltage is maximum, power will be maximum, but the voltage, output voltage is going to start dropping down. If that's 10 volts, where would you think the half power point would be? No, half power. So it's going to be somewhere up this slope. It's going to be the same place on this slope, right? You understand? So here we would deliver maximum power. Bandwidth is described as where the media itself drops 50% of the power that's available. We call this bandwidth. So everything out there responds to a frequency. High frequencies and low frequencies, and they call things to happen. So what we're doing is somehow the guys are limiting you to what we call a bandwidth, and that's how much they're giving you, right? It don't have to start at 0. It can be somewhere up here where it starts working and don't work. But we say the bandwidth, the cutoff frequencies, when this thing says it's not giving us enough power to do anything, it's designed is when the output power drops down to 50%. And of course, what's controlling the power right now is how much voltage we apply to the circuit. We measure voltage all the time. Voltage is the easiest thing to measure in an active circuit. We don't measure current that often. Why? You got to break the circuit. True current, you know. So we don't measure resistance in an active circuit. So 90% of our measurements in an active circuit when we're trying to figure out how things operate and troubleshoot is going to be what? Voltage. So what we do is most of our measurements, we have to relate what's going on with the current with this voltage. What's going on with this voltage, right? You understand? So when they get to transmitting information over some type of media, every media's got a bandwidth to it. Everything's got a band. How much information can we put through that media and not have it drop everything, right? You understand? So what they defined is that when the power drops down to 50%, so let's say 10 volts gave me 100 watts. Well, when this guy got down to 50 watts, we would say it's cut off. It's bad. I mean, we wouldn't operate it above, we won't operate it above cutoff, right? You understand? So how would we calculate that? What voltage would that be? If 10 volts gives us 100 watts, what voltage would give us 50 watts? Huh? Power varies with the square. It don't vary in half. If I half the voltage, I'm not going to get 50 watts. I'm going to get 25 watts. Right? You understand? So let's see this. Let's say 10 amps times 10 amps. This would give us what? Gives us 100 watts. Let's say power out is equal to 0.707. It goes out a lot further than this, times 0.707. Have y'all heard that before? 0.707? What's that? I'm sorry. Let me redo that. It's not 0.707. It's 70.7%. So let's do 7.07 times 7.07. What's that give us? Actually, 0.7 goes out a lot further, right? This is just what we use. It should give us 49 watts, but actually, actually it's 50 watts if you carry the 0.707 out, right? You understand that? So we take that right there, we multiply by 0.707. So 70.7% of the maximum voltage, which would be up here somewhere, this is where the cutoff frequency would be. So if I was looking at the power curve, it would be 50 watts, right? You understand that? But we're not looking. I mean, I'm sorry. Yeah, it would be 50 watts. But if I'm looking at the voltage curve, it's going to be 70.7% times 0.707. Your maximum voltage times 0.707. And we call this the cutoff frequency. All over the place. So the bandwidth would be, and I don't know if we'll get to calculating the actual bandwidth of a circuit, but inside your data sheet, it's called the bandwidth product, I think. If you've still got your data sheet up. Current gain bandwidth product. So we use this in calculating the upper bandwidth of the transistor. For a transistor, guys, when you got a high enough frequency, it'll couple through anything. And pretty soon the base is going to bypass the junction. It's going to jump through it, right? You understand? And at that point, the power that we can get out of that transistor is going to drop down. So this is what we do. We use this guy right here to calculate F2 for this transistor. And that would tell me the highest frequency I could operate that transistor at, right? So right now it's saying could be anywhere between 300 and what? Minimum of what? 300, and we can calculate the maximum. This gives us the actual input capacitance. If you hadn't had AC, it's not going to make much difference. This is what we use. So this is what we use to actually calculate the bandwidth. What frequency range can this transistor operate in? So what's the range of the human ear? What can we hear? What's our bandwidth? Well, some people run themselves. But usually, you know, we can get down, we can hear probably around 15 hertz, maybe 30 hertz. And then your upper bandwidth is around 15,000. Most people start losing their hearing about 15,000. They don't mean it's there. So dog whistles are just what? They're up above our bandwidth, right? We can't hear it. Our ears attenuated. It can't handle that, right? That makes sense. And this is switching characteristics. Unfortunately, a transistor, when we switch it, we'll come back to this in a minute. Because I wanted to show you something about DD. So when we switch a transistor, okay, and here we're going to have what? 0.7. and we saturate the transistor, and it drops 200 millivolts, right? You understand? That means we have 200 millivolts right here. What's the problem? Yeah, well, we looked up this transistor and it says it's going to saturate somewhere between, what was it? Are y'all looking at that sheet? VCE saturation, saturated. 200. So if this dropping 200 millivolts, that means relative to circuit common, this is going to be sitting at 200 millivolts. This is sitting at 700 millivolts. How are we supposed to bias the base to emitter? How's it supposed to be biased? Or bias or reverse bias? To make a transistor operate within its active region, how do we have to bias the transistor? You just can't say reverse. We got 3 leads on the phone. We're gonna reverse bias all of them? That'd be cut off. So how are we supposed to operate? How do we forward bias an NPN transistor? Let's say this is the collector, this is the base, and this is the emitter. How are we supposed to operate that thing? This one right here is supposed to be forward bias. This one right here is supposed to be reverse bias. Because that's what's happening is the collectors pulling those things through. Well, what do you notice what happens when we saturate? So it means this is supposed to be a little plus and this is supposed to be a big plus, right? You understand? So we're moving toward reverse bias. It's not totally reverse bias, but we're definitely moving for it. Well, what happens is this causes a charge to build up between the base and the collector. And then when you cut this thing off, that charge has to dissipate before the transistor cuts off. And they call it a storage time. So we can cut it on real fast, but we can't cut it off real fast, right? You understand? You can turn the base off, and if we had something that was fast enough, you'd see that the collector sets at 0 for a while before it goes back to the plus voltage. So that's what we're talking about here, using this thing as a switch. Delay. So this could give us up to a watt. No, up to what? 200 nanofarad. Between when we tell it to cut off and when it actually cuts off. This is one of the advantages some of our FETs have over bipolars is we can saturate them and cut them off fast. But FETs just can't handle the power and the current a bipolar transistor can. So these guys have different features that would tell you where you wanted to use them at. So this is what we would use if I was an engineer and I'm designing a switch. Delay time, rise time, fall time, storage time. What we have to understand is nothing turns on instantly and nothing turns off instantly. So when we draw digital, we usually draw it like this, right? But if I was to spread this out, what we would see, it actually looks like this. So it takes time to cut it off, and it takes time to do what? Cut it on. Because here we're looking at voltage collector to emitter. So it actually has a storage time. We call this time right here rise time. We call this fall time. And we actually measure it between 10 and 90%. Now they do that because most of the time when we saturate these things really fast, it comes over here and it does this kind of stuff. And then when we cut it off, it'll come down here and actually do this kind of stuff. You know, whether you understand it or not, that's determined by the amount of capacitance and inductance in our circuit. So that means we choose 90% of this and 100%, and the time it takes for the signal to go from this to this, we call this what? Rise time. And this right here is what? And you'll get into this and all type of digital stuff. So we're operating this thing in a digital capacity, which means it's what? It's either all or on. So that's the data sheet. By the way, the power would be what's the log of a -3? Yeah, -3. What's that? You get a log on a minus dB? A minus, huh? Oh, I'm sorry. 3 dB. So what would we do? We would take 10 and raise it to a minus 0.3, right? So what'd you get? It's got to be a fraction. Huh? Anything, when you raise 10 to a minus number, you're going to get a fraction. When you raise it to a positive number, you're going to get a number, right? We did something wrong. Let's see. I got to figure out what we're doing wrong. It's supposed to come up again. It's supposed to come up. If we did it right, it would come up and give us a 0.707. I'm trying to figure out what I'm doing wrong. Because 50% power is a minus 3 dB drop in voltage. So let's see if that comes up to be 0.5. It did, right? So the first answer we got was right. So what did y'all do? You took 0.3, right? Okay. I'm sorry. So this is dB, 3 dB. Okay. Then we shift the decimal point to the right one spot. So that would give us a minus 0.3. And then if we take that, it comes up. Sorry.
That's part of it.
Yeah. 0.5.
You raise it.
Yeah, because it's a log. It's 30. It's minus 3 dB. So minus 3 dB on our voltage, would respond to 50% of the power. So a lot of people say the bandwidth is minus 3 dB. So we give loss in communication systems as dB loss. We get separation on the amplifier between your left and right channel. They give you a dB rating on that. You want a real high dB rating on your left and right channel, right? Because what that means is how much of your left channel gets into your right channel, or how much your right channel gets into your left channel. Because we've got all this AC floating around. And AC, guys, if you take AC current will couple through anything. The higher the frequency, the more it's going to couple through, because we call it capacitive effect. So to get a capacitor, all you need is 2 conductors that run side to side, and you've got some type of insulator beside them. Right?
That's the same as you get. They gave it to the
Oh, okay. When you said 5, you didn't. I don't remember you saying milli, but you're right. I didn't hear you say milli. I heard you say 500. So I didn't hear the milli. So when you're looking for a stereo amplifier, for your separation between your right and left channels, you want it to be real high, right? You understand? Because that's how much signal will go between the two. You want a lot of dB. That makes sense? If you're into stereo equipment, high quality stereo equipment, some of the things you're going to look at is that, the channel separation, the power, what you need, all that kind of stuff, right? And sometimes when they give you the wattage rating on those things, they're the wattage rating into one speaker. If you put it into 2, you basically got half your power, so you got to be careful. So what we'll look at next. It looks like we don't have time to do any lab, so let's go back. Y'all got any questions on what we went forward? I want to look at we got a worksheet on saturated switches. Yeah. And what I'll do instead of starting the other part, now we got a lab on saturated switches. So,